Hello everyone. Today is going to be a big day. We are going to be looking at estimating areas under curves and properties of sigma notation, two seemingly unrelated concepts, but hopefully it will all become clear when they come together to give us a precise method to determine areas under curves and beyond. So we're going to start with this. So in the past we've been able to determine the area of regions bounded by straight sides such as rectangles, triangles, and trapezoids. But how do we determine the area of a region with curved sides? This is the second big idea of calculus. So if a graph is a positive function, so it lies above the x-axis, and the area under the curve from A to B, where A is to the left of B, is defined by the region below the graph, above the x-axis, to the right of A, and to the left of B, how do we determine the area of this region? So we can approximate the area by dividing it into vertical strips of equal width, as shown here, and approximating the area of each strip with a trapezoid. So we'll be using trapezoids that have two adjacent right angles, as shown here, and we have seen this formula for the area of a trapezoid fairly recently. So moving on to example number 1, we're going to estimate the area under this curve from 2 to 8 by dividing the region into 3 vertical strips of equal width and approximating the area using trapezoids. We're going to write our answer as a simplified exact value and then round it to the nearest hundredth if root 2 is that and root 6 is that. So before we get into this question, let's maybe see if we can get an approximate result from our calculators. So we can start by graphing this function, see what it looks like, and we can calculate the area under the curve using this function. So we need to pick a lower limit of 2. Now it doesn't look like we can pick exactly 2, but maybe we'll pick something close. And we'll go up to 8 as required. So that's roughly 8. We're going to see what happens. So we get a result of 46.84-ish. So I guess that's what we're going to shoot for with our result in trapezoids. You may be surprised to know that this limitation on the precision of my lower and upper limits is actually probably intentional, and this could be improved along with many other things on this calculator, but this is actually one of the few products that succeeds by staying the same, as you can find out on an episode of the Planet Money podcast titled The Calculator That Time Forgot. There's a link in the description. So here's my graph. I've done 3 root x plus 1 and overlaid 3 trapezoids. The width of each of these trapezoids is 2, and we need to determine the heights in a moment. If you were to zoom in on one of these areas, you would start to see that this method is far from perfect, much like our calculators, but hopefully will come close to the actual result. So next we're going to determine the heights at each of these points for the trapezoids. So each corresponding value of y is going to be determined using our function, 3 root x plus 1. So I'm going to sub in 2 for x here, so that'll give me 3 root 2 plus 1. Next I'm going to sub in 4, so it'll be 3 root 4 plus 1. 3 root 4 will be 6 plus 1, giving me 7. Sub in 6 for x will be 3 root 6 plus 1. And last, 3 root 8 plus 1, we can simplify to 6 root 2 plus 1. So now that we have all of our heights, this is 3 root 2 plus 1, this is 7, this is 3 root 6 plus 1, and this is 6 root 2 plus 1. Now that we have those, we can figure out the area of each of these trapezoids. So area 1 is going to be 1/2 times the height, which is 2, times b1 plus b2. So it'll be 3 root 2 plus 1 plus 7. Now 2 divided by 2 is 1, so we're left with basically just this. So it'll be 3 root 2 plus 8. So area 2 is going to be 1/2 times h, which is 2, times b1, 7, plus b2, 3 root 6 plus 1. So this will simplify to give 3 root 6 plus 8. For area 3, we're going to have 1/2 times h, which is 2 again, times 3 root 6 plus 1, plus 6 root 2 plus 1, and we'll simplify that a little bit. 2 divided by 2 is 1. Add the 1's together, so we're going to have 3 root 6 plus 6 root 2 plus 2. So now that we have our three little areas, we're going to add them up, a1 plus a2 plus a3, and we'll eventually get 9 root 2 plus 6 root 6 plus 18. So we just add the root 2's together. 3 plus 6 is 9. Add the root 6's together. 3 plus 3 is 6. And add the rest together. 8 plus 8 plus 2 is 18. So that's exact, which would approximately be, if you type this into your calculator, 45.42-ish. But using the approximation given in the question, using 1.41 and 2.45, we would get approximately 45.39 instead. So onto the back page. To approximate the area under the curve f of x from x equals a to x equals b, using n trapezoids of equal height, we are going to first need to determine the h's. So in order to figure out what this h is for each trapezoid, we need to figure out this full distance, which would be b minus a, and divide it equally into n pieces. So we divide by n. Next, we need to determine the approximate x values between a and b. So the first x value will be a. The next x value will be a plus h, so that's the one here. The next x value will be a plus 2h, and so on. And then each of these heights would be given by f at those x values. So this is h, that's f at a, that's f at a plus h, that's f at a plus 2h, and so on. So we are going to make use of our trapezoid formula, which is this one, b1 plus b2 over 2 times h. So first off, we can use these values for y, and we're going to go between a and a plus h. So first off, we're going to have f at a plus f at x1, so that's a plus h. Divide that by 2, multiply that by h. And then we need to add the second trapezoid, which will be given by f at x1 plus f at x2 divided by 2 times h. And then we would have f at x2 plus f at x3 divided by 2 times h. And then we'd have all the way down the line until we got to f at x n minus 1 plus f at b divided by 2 times h. And hopefully you can still see that. So we can simplify this a little bit. We can factor out a h from all of these terms. We can factor out a 1/2 from all of those terms. So we can go 1/2 h. And then we have 1 f at a. We have 2 f at x1s. And we would have 2 f at x2s all the way along until we got to just a single f at b. So if we tweak this a little bit, expressing h as b minus a over n, b minus a over n, this is what we have on our formula sheets. So f at a plus 2 f at x1 plus so on plus f at b. So next example, we're going to approximate the area under the curve sine x from 0 to pi using 6 trapezoids, and we're going to write the answer as a simplified exact value. So if we are using 6 trapezoids, that means n equals 6, and we can use our formula that we've just developed. So we will have a equals 1/2 b minus a, b is pi, a is 0, divided by n, which is 6, and then we're going to go f at 0 plus 2 f at pi over 6 plus 2 f at pi over 3 plus 2 f at pi over 2 plus 2 f at 2 pi over 3 plus 2 f at 5 pi over 6 plus f at pi. So this would be like 1 over 6, 2 out of 6, 3 out of 6, and so on. That's where all these came from. Next, pi over 6 times 1/2 goes to pi over 12. And now sine at 0 is 0, based on our unit circle knowledge. Sine at pi over 6 is 1/2, again based on our unit circle knowledge. Sine at pi over 3 is root 3 over 2. Sine at pi over 2 is 1. Sine at 2 pi over 3 is root 3 over 2. Sine at 5 pi over 6 is 1/2. And sine at pi is 0. So we can combine all these together, what we can. So we will simplify to 1 plus root 3 plus 2 plus root 3 plus 1. And further, we would end up with pi over 12, 4 plus 2 root 3. So we can factor out a 2 from the bracket here, giving us 2 pi over 12, which simplifies to pi over 6. And in the brackets, we're left with 2 plus root 3. And this is approximately equal to 1.954, which is reasonably close to the actual result, which is 2, but we'll save how to do that for another video. Next topic, properties of sigma notation and formulas for special sums. So sigma notation, remember that the sum of ti from 1 to n can be written like this. We start from 1 and go up all the way to n, and the sigma means add. So a few properties of sigma notation we will develop right now. The sum of this from I equals 1 to n, so there's nothing really being iterated here, it's just c the whole way through, n times. So we would basically have c plus c plus c all the way up to an nth c, so 1, 2, 3, and so on to n. So we basically have nc. Next, the sum of cti from 1 to n. So the first term would be ct1, second term would be ct2, and so on, all the way up to ctn. Notice there is a c in each of these terms, so we can factor that out, giving us t1 plus t2 all the way up to tn, which we can write more simply as c ti from I equals 1 to n. Next term, the sum of ti plus or minus si from 1 to n. This plus or minus is just telling us it could either be a plus or a minus, so really we could do this for two different expressions, ti plus si and ti minus si. So rather than do that for two separate expressions, we're just going to do it a little more compactly with this notation. So the first term would be t1 plus or minus s1. The next term would be t2 plus or minus s2. And then t3 plus or minus s3, and so on, all the way to the nth term, which would be tn plus or minus sn. Now we can group all the t's together, so we would have t1 plus t2 all the way to tn, and we can group all the s's together, so we would have plus or minus s1 plus s2 all the way to sn, and we can write this more compactly by going sum of ti from 1 to n, and we can write this more compactly by going the sum of si from 1 to n, and it's plus or minus. Next, looking at formulas for special sums. Special sum number 1, what type of series is this? So we're going to write out a few terms here. The first term would be t1 plus 0, because we're starting at I equals 1. The second term would be t1 plus d. The third term would be t1 plus 2d, and so on, all the way to n. So the nth term would be t1 plus n minus 1 times d. Now this should hopefully look very familiar. we have Tn equals T1 plus n minus 1 times d, and that is an arithmetic series. We also had a formula for this, which was Sn equals n over 2 T1 plus Tn, or equivalently, n over 2 T1 plus n minus 1 times d. Now, because this is essentially identical to this, we can write this expression, this nth partial sum, as just n over 2 times 2t1 plus n minus 1 times d. Looking at special sum number 2, what type of series is this if r is a constant? So let's go ahead and write out a few terms. So the first term would be t1, r to the 0, which would just be 1. The second term would be t1 times r to the 1. The third term would be t1 times r squared, and so on, to the nth term, which would be t1 r to the n minus 1. Now we can factor out a t1 from each of these, and we would be left with 1 plus r1, r to the 1, plus r to the 2, plus r to the 3, and so on. So that would basically be r to the I minus 1, I equals 1, n. If we're looking at a series that goes 1 plus r to the 1, plus r to the 2, plus r to the 3, this is a geometric series. And we can write this partial sum with t1 r to the n minus 1 over r to the 1. And hopefully that formula looks somewhat familiar. So in special sum number 3, what does the series I from 1 to n represent? The first few terms would look like this, all the way to n. So this is the sum of natural numbers. And the nth partial sum of this would be represented by n times n plus 1 divided by 2. And this is on your formula sheet. Special sum number 4, what does the series I squared from 1 to n represent? So we would go 1, 4, 9, and so on. This is the sum of natural numbers squared. An expression for the nth partial sum of this is given by n times n plus 1 times 2n plus 1 divided by 6, which is also on your formula sheet. Special sum number 5, I cubed from 1 to n, we would go 1 plus 2 cubed plus and so on. So this is the sum of natural numbers cubed. And an expression for the nth partial sum of this is given by n squared, n plus 1 squared over 4. So part C, we're going to look at some examples for finding sums of finite series. So first off, I cubed plus 5. So we can split this up like this. I cubed, using our property from the first page we looked at. We know the nth partial sum of natural numbers squared looks like this from the previous page. So we just need to sub in 10 everywhere we see an n for that one. And in this one, we would have 10 occurrences of a 5. So it would be 5 plus 5 plus 5, 10 times. So then we have 10 squared, 11 squared over 4 plus 10 times 5. And this would give us 100 times 121 divided by 4 plus 50. And eventually we would get to 3075 with this sum. In part B, we're doing this from 1 to 20. So we can expand this, so FOIL it, from 1 to 20. That would be 4i squared minus 6i plus 9. And we can use the property of sigma and go like this. So 4i squared from 1 to 20 minus 6 plus 9. So we have an expression for I squared from the first page that was given by n times n plus 1 times 2n plus 1 over 6. And we're going to sub a 20 in there. So we would have 20 times 21 times 41 divided by 6. And then we would have subtract 6. We have an expression for this as well. This is given by n times n plus 1 over 2. We sub in a 20 everywhere we see an n. So we'd have 20 times 21 over 2. And then this would just be 9 plus 9 plus 9 until we get up to 20. So that would be 20 times 9. And then we can simplify this a little bit. So we would get 11,480, subtract 1,260 plus 180, and that eventually gets us to 10,400. So on to the last set of examples. We're looking at finding sums of infinite series. So this sum, as n approaches infinity, if we maybe look at it instead for a smaller one like 10, this sum would look like 1 over 10 squared times 1 plus 2 plus 3 all the way up to 10. So this number is static, so whatever number we reach at the top of our sum is going to be common for all of these terms. So we can basically just factor that out. So that's what we're going to do now for this actual sum here. So we're going to take out a 1 over n squared from the sigma. So we're going to have limit as n approaches infinity, 1 over n squared, because that's just a constant. And then the sum of I from I equals 1 to n. And we have an expression to deal with this. It is given by n times n plus 1 over 2. So we're going to sub that in for there. So next we're going to go limit n approaches infinity, 1 over n squared times n plus 1 over 2. And we can clean this up a little bit. So inside here it would be n squared plus n. And if we're dividing that whole thing by n squared, maybe what we could even do is get rid of that and one of those. So then we would have 1/2 n plus 1 all over n, which is the same as 1/2 n over n is 1 over n. So as n approaches infinity, this term will go to 0, that term will be unaffected, and our sum is 1/2. So onto this last sum, we are going to try to factor this out. So remember, if we did this sum simpler from 1 to 10, what we would have is 2 times 1 squared over 10 cubed plus 2 times 2 squared over 10 cubed plus all the way up to 2 times 10 squared over 10 cubed. So what we can do basically with this n cubed is factor it out of, like, remove it from the sigma. So that's what we're going to do. Limit as n approaches infinity. We're going to factor the 2 out as well from the sigma. So we have 2 over n cubed and the sum of just I squared from I equals 1 to n. So we have an expression for this that we can substitute, which is n times n plus 1 times 2n plus 1 over 6. So next we'll get n approaches infinity, 2 over n cubed times n plus 1, 2n plus 1 over 6. So I'm going to remove one factor here. That's going to become an n squared. I can factor this out from the brackets and go 2 over 6, which reduces to 1/3, which I can take out front. So now I have a limit as n approaches infinity. I'll put the 1 over n squared in there. This will expand to 2n squared plus 3n plus 2. and this n squared is dividing each term individually. So we can write what that would look like. So we would get 2 plus 3 over n plus 2 over n squared. And as n approaches infinity, that term will go to 0, and that term will go to 0 as well. So the limit as n approaches infinity of 2 is just 2, and we end up with 2/3. So that's it from me for today. I would encourage you guys to try these questions out on your own. See you next time.